What if we have more than 2 samples of numerical data? What if I have 3 samples? What if I have 4 samples? What if I have 10 or 20? What if I want to know whether there's a difference between the means of the populations that all these different samples are drawn from? That's a common problem, and we can do that with a method called ANOVA. For example, suppose I give different amounts of water to 5 different groups of potato plants. And then I measured how many pounds of potatoes produced by each plant, and I want to know whether the different amounts of water made any difference in the end. Suppose I'm producing batches of semiconductors and adding 4 different amounts of some doping agent, and then I measure the conductivity of each resulting element of my samples. Suppose I have 4 groups of people, subjects who exercise for different amounts each day. One group exercises for 10 minutes a day, one for 20 minutes a day, one for 30 minutes a day, etc. And then after several months, we measure how much their blood pressure changes. We see if these different methods of different amounts of exercise cause blood pressure to change and maybe hopefully reduce people's blood pressure. These are all examples where we would want to analyze our data with ANOVA. So, first of all, we need to know, when can I use ANOVA? All of these different methods have their limitations. So this one is very specific. Like almost all the other methods, every observation must be independent of all the others, so that's important. Data within each group must be at least approximately normally distributed, so that's important as well. You need at least a kind of a mound-shaped, a bell curve-shaped sort of distribution. Each of the groups need to have similar variability. They can't have enormously different standard deviations. And if those 3 conditions are met, then it's probably a good idea to use an ANOVA method. ANOVA is a hypothesis testing method. It's not something we can get a confidence interval out of, but it's all based on a null hypothesis. And the null hypothesis is that all these different groups have the same mean population average. And there's a bunch of complicated stuff in the middle, and in the end, it's going to spit out a p-value. No, the p-value is, well, the same thing it always is. The p-value is the probability of getting what we got, or something more extreme, more interesting, getting differences as big or bigger than what we got, assuming that the null hypothesis is true. So if the p-value is really, really, really small, it tells us it would be very unlikely to get results like this if the null hypothesis were true. So therefore, we can conclude the null hypothesis is not true. If our p-value is large, then it says, well, this would be a typical result if the null hypothesis were true, and so we can draw no conclusions and we fail to reject the null hypothesis. All right, so ANOVA is an acronym. It stands for Analysis of Variance. Variance meaning, in a statistical sense, variance as in standard deviation squared. So let's take a minute and remember exactly what standard deviation is and what variance is, where they come from, how we get those. So if I just had a list of numbers and I wanted to compute the standard deviation or the variance by hand, first, I would need to take the average, the mean of that list of numbers, and then I would subtract the mean from each number on the list. This would give me the residual, also sometimes called the error. So if my number was above average, the error, the residual will be positive. If my number was below average, then I'll get a negative residual. Now, in this case, I want to measure the spread, how spread out, how scattered these numbers are. So I don't care whether they're above or below average. I just want to see how far they are from average. So we square each residual. That makes the negatives become positive. Then we add up the sum of the squares of the residuals, sum of the squares of the errors. That gives us a value we're going to call SS, the sum of the squares. Then we can divide the sum of the squares by the number of degrees of freedom to compute an average, but not by, we'll do the degrees of freedom, so that's usually going to be the sample size minus 1. And this then gives us the variance. That's how you would compute a variance by hand, also known as the mean square error, MSE. If I want the standard deviation, I then take the square root of this. And that's how we could find a square root by hand. All right, so ANOVA is based on that idea. Since it's analysis of variance. First of all, it says, suppose we put all the samples together and we found the total sum of the squares of all the residuals, the sum of the square. Okay, and ANOVA is, now let's take that and let's partition that into two different pieces. First of all, we're going to find the part of this which comes from variation between the different groups. That will give us the MSG, the mean of the squares of the residuals between the groups. So in order to do that, what we'll do is, if I wanted to do this by hand, and we're not going to do this by hand, we're going to do this automated, but I need to at least walk you through the process. What would happen if I did this by hand? I would take all my different groups and I would replace every number in all these different groups with just the average, the mean of its group. So that if the average of this group is 3.4, I'd replace all those numbers with 3.4. So then I've got all my different groups, and the groups have different averages, but within the group I've ironed out all the variation. Then I would subtract the overall mean of the whole entire, all my group of all my elements and all my samples. I would then square the residuals, I would add up, and then what do I divide this by? In order to get the variance, the mean of the squares of the residuals, I would divide this by the number of groups minus 1. So that's the degrees of freedom based on the number of groups. And that gives me MSG, the mean of the squares of the residuals between the groups. Next, I would find the part of the sum of the squares of the residuals, which comes from variation within the groups. So that's going to give me MSE, the mean square error. Now what I'm going to do is I'm going to take the mean of each group and subtract it from each value within that group. I would then square these residuals, add them up, and this time I will divide by the total number of all my different, total number of everything I've got, all my data points, minus the number of groups. Then what we'll do is we take the ratio of these things. MSG divided by MSE, the mean squares based on the variation between groups, and then the mean square error, mean square based on the variation within the groups. And that gives me F, and F is my test statistic. This is a new kind of test statistic. It's not a Z test statistic. It's not a T test statistic. It's not a chi-squared test statistic. This is a new test statistic based on a new distribution, the F distribution. So let's do a nice specific example. Here's an interesting paper I was reading. The paper was comparing different espresso coffee brewing techniques published in the Journal of Food Engineering, and they did a whole bunch of studies on this, but one little bit of data we're going to look at is where they compared the amount of foam produced. They had 3 different espresso brewing methods, and then in each case they figured how much foam they produced. So in this case, they did 9 cups of espresso coffee produced using each of 3 brewing methods. The bar, using a bar machine, using the hyper espresso method, and the espresso system. They used exactly the same batch of roasted coffee, the same water, the same operative settings were used in each case. Everything's held constant except for the different method. And then for each cup, they measured the foam to liquid ratio as a percentage. So 30 seconds after extraction. So you get your cup of coffee, you wait 30 seconds for it to settle down, and then you calculate, the foam we've got is, say, 50% of the liquid, that sort of thing. So again, step 1, before we do anything complicated, we need to play with the data. We need to examine the data. So here are all my R commands for doing all that, getting the mean and the standard deviation and the 5-number summaries. In this case, I think it's particularly useful to make a side-by-side box plots of this. I think they're really useful. So notice what I've got up here. I say plot, open parenthesis, and then espresso is the name of my data frame, $, foam index. That's my response variable. That's my numbers. My numbers are all in the foam index column. And then I put a tilde. That's a little twiddle sort of sign. You find it in the upper left part of your keyboard, usually just to the left of the number 1 button. And you press shift, and then you get that little twiddle sign. That tells me in R, that says I want to look at this thing is caused by that thing. So I'm looking at foam index as being caused by espresso method. And then espresso method, that's the column where we just list these different methods, bar, the hyper, and the espresso method. And so it gives me these side-by-side box plots. And this looks pretty good. It looks like we've got some pretty good different things going on here. Notice that the bar method and the hyper method, they don't overlap at all. In the hyper method, every single data point was more than every single data point in the bar method. So hopefully we get statistical significance out of that. The espresso method overlaps a little bit with those. So let's see what we can get out of these things. we're going to run ANOVA inside of R. This is, ANOVA is not something we're going to do by hand. So we're going to let R do all the details of all the particular calculations for us, and that's fine. At this point, we need to know the general idea of it. As long as we understand the null hypothesis and then can interpret the p-value that comes out of it, we can make sense of this, even if we don't know all of the details that go inside of it. So here's what we do. Here's the lovely R command. First of all, we're going to use the summary command and apply that to AOV. That means analysis of variance. And then we've got the same sort of thing. Espresso $foam index, tilde sign, espresso $ method, seeing the foam index as being caused by method. And this produces an ANOVA table. Now, different pieces of software will do this in different ways, but ultimately they all will spit out an ANOVA table. So the first column in the ANOVA table here is DF, degrees of freedom. Notice that the number we have here is 2. We tried 3 different methods, and so we subtract 1 from that, and so there are 2 methods. All right, so that's fine. And then we had a total of, let's see, it was 9 cups of coffee using each of 3 methods. So we had a total of 27 data points. 27 cups of coffee were measured. So the degrees of freedom based on the residuals, based on the errors in this case, is 24. 27 cups of coffee, 9 times 3 is 27. 27 cups of coffee minus our 3 methods. So for each method, we had basically, in each method, we had 9 cups of coffee minus 1 is 8. 8 times 3 is 24. So there's our 24. So our 2 degrees of freedom are 2 and 24. Next, R goes through and calculates the sums of the squares of all this sort of thing. On the bottom, we have the sums of the squares of the residuals, and on the top, we have the sums of the squares of the sums of the squares based on the 3 different methods. And notice that we get a bigger method, bigger sums of squares based on the method than we do with the residuals. Now we need to take those and compute the mean squared. So for instance, in the top row, we're going to compute a variance. A variance is a mean square residual. So we take 4,065 divided by 2 gives us 2,032, I guess 0.6. There must have been some decimals running around there they didn't list. And then similarly, we take that number, 1,717 divided by 24. And so that gives us the variance from the different parts of these variants. The variance from variation within group, the mean squares of the errors, MSE in this case is 71.5, and then the mean squares of between the groups, MSG, is 2,032.6. So that looks a lot bigger than 71. So that's hopefully that's going to be statistically significant. And then to get our F value, our F test statistic, we take the ratio of those two things. 2,032.6 divided by 71.5 gives us a test statistic, an F value of 28.41. And then based on that test statistic, we can compute a p-value, which in this case is 4.7 times 10 to the minus 7, which is really, 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 really small. And so notice it puts 3 stars by that, saying it's significant at the 0.001 level. So that means it's very, very, very significant. And so as a result, we have a statistically significant difference in the amount of foams produced by these 3 different brewing methods. All right, we need to talk a little bit more about this F distribution if we're going to understand all of that. This is what comes out of the ANOVA analysis. So F is produced by the ratio of 2 different variances. Variance in the sense meaning a standard deviation squared. This means that F is strictly positive. You could never have a negative variance, so it's the ratio of 2 different numbers. F, now because it's 2 different variances, every variance has its own degrees of freedom, so F is based on, has 2 degrees of freedom associated with it. One for the numerator's degree of freedom, one for the denominator's degrees of freedom. This also means ANOVA is always going to give us a right-tailed test, because if there's a big difference between these groups, then the numerator is going to be bigger than the denominator. So that's always going to push us to the right towards larger values. So that means when we compute a p-value, it's always going to be a one-sided test, a right-tailed test. We want to know the probability of getting what we got or more. R, as always, gives us probabilities of this or less, so we need to do 1 minus. So if I wanted to do this semi-manually in R, I would do 1 minus PF, probability from the F distribution, of our test statistic, 28.41, comma 2, degrees of freedom of the numerator, comma 24, degrees of freedom of the denominator, and hey, lo and behold, there's that same p-value that R gave us automatically. So an ANOVA analysis is wonderful, but like any hypothesis test, at the end, I get one of two results. We either reject the null hypothesis and say we have something statistically significant here, or we don't. We get one bit of data, yes or no. I want to know more information than that. Well, which group is different from which group? ANOVA does not tell me that directly. So after I've done an ANOVA analysis and I got something statistically significant, then I want to compare these three different groups. In this case, I have three different groups, and then I want to compare each group with each of the other two. So in this case, we'll make three comparisons. Now, this can get complicated if I've got like 10 groups or something like that. But there's a method of comparing these different groups and putting some confidence intervals on these and assessing how different various groups are between each others. And this is the Tukey HSD group, as developed by John Tukey many years ago. We notice here's my R command. So we apply Tukey HSD on a significant difference group, the difference test to the AOV, and then there's the same thing, espresso foam index tilde espresso method. And then it runs the test on this. It's assuming we're doing a 95% confidence level. And notice down here, the meat of things are down in this table. So it finds what's the mean difference between these two groups. It puts a confidence interval on the difference between these groups, and then it gives me a p-value, an adjusted p-value, based on the null hypothesis that there's no difference. You notice that the smallest p-value comes from comparing the hyper method with the bar method. So each row of this compares one group with another group. So the first row of this table compares the hyper group with the bar, hyper method with the bar method. We get a really, really small, so we have a statistically significant difference between that. And we can find that the mean difference is somewhere between 18 and 38. On the other hand, if I go to the next comparison, the I espresso method with the bar method, that p-value is 0.18. That's not statistically significant. That's more than 0.05. So this data, these 9 cups of coffee from each method, are not enough to establish that there's a difference between those two methods. On the other hand, if I go to the I espresso method and compare that with the hyper method, then yeah, look at that. That's a statistically significant p-value, 0.0000419. That is indeed less than 5%. And so that tells me that that one, okay, that we've got a statistically significant difference there. The hyper method is essentially different than the other two, but I espresso and bar don't, at least this data doesn't establish a statistically significant difference between those two. All right, so here's a summary. ANOVA is a method for comparing 3 or more groups of numerical data. It's based on the null hypothesis that all the groups have the same overall population mean, and any variations are just due to random chance in picking up these samples. ANOVA gives me a p-value based on this new distribution, the F distribution. The F-test statistic comes from the ratio between two variances, where I've got MSG, which is the mean square variance between groups, and MSE is the mean square error. That's the variance based on variation within the groups. And so if I get a big number, that means my two groups, at least two of the groups are very different than each other. And if I get a small number, it means that the differences between the groups are small relative to the variation within the groups. And then once we've got that, if we get a statistically significant difference, and then I want to know which groups are different from which other groups, we can run a Tukey HSD analysis, and that can tell me something about which ones are different from which other ones.